Every time I see something that looks like a Wheatstone bridge, I start to panic. It's like, I'm not going to be able to do this problem. But it's not bad. Okay, so here we are going to determine VC of t given that the switch had been closed for a long time prior to t equals 0. So if it had been closed for a long time, let's take a look at what that would look like. Maybe I panic because I can't draw them. Okay, so we want to think about the things that we need. We need VC at 0, which is the same at VC at 0 minus, which is why we draw this. We need VC at infinity, and we need the time constant, which is R equivalent C, where R equivalent is the Thevenin equivalent of the resistance during the time period that we're looking at. So right now we're looking for VC of 0, so we're looking for the voltage across this capacitor. So what we really need to know is we need to know the voltage here and the voltage here, and then VC of 0 will be V plus minus V minus. So let's first notice we do have a current. Let's first go ahead and figure out, this is how I did it. There's lots of ways to do it. There's not just one right way. This may or may not be the best way. And make sure it's the way I did it, because I like to do things a different way than my notes and then mess them up. This looks like the way I did it. Okay, so let's find the current going here. So I'm going to find that current. And so to do that, I want to find the equivalent resistance of this part right here. Notice that without the capacitor there, because it's been a long time, so that's an open circuit, this is the same as 2 3 kilo ohm resistors in parallel. So this is a 3 kilo ohm, so this is a 3 kilo ohm resistor, and this is a 3 kilo ohm resistor if we look at it that way. And so then 3 kilo ohms in parallel with 3 kilo ohms is 1.5 kilo ohms, because if you have identical resistors in parallel, the equivalent resistance is just half of them. So then this circuit is equivalent to this circuit in terms of finding the current. So if I want to find the current here and just use Ohm's law, V equals IR, 20 equals I times my total resistance here is 2.5, which gets me that I is 8 amps. Okay, so now I know that the current coming through up here is 8 amps. Okay, so let's see what I did. Okay, so I'm going to redraw it. This is almost certainly not the most efficient way to do this, but it's the way that made sense to me at the time. Okay, so this is 1 kilo ohm. This is 20 volts. So, and let's make this ground. And we have a current of 8 amps. going that way. And so as we go across the 1 kilo ohm resistor, Ohm's law tells us is that 8 amps or 8 milliamps? Yeah, this was that was 2.5 kilo ohms. This was, so this is 8 milliamps. Those kilo ohms. This is milliamps. So 8 milliamps times 1 kilo ohm, so that's 8 volts. So that means that after going across this resistor, we've dropped 8 volts. So that means the voltage right here is now 12 volts. Okay, now I can see that my current, each branch here, this is 1 kilo ohm, this is 2 kilo ohms, this is 2 kilo ohms, this is 1 kilo ohm. I can see that each branch all the way down is 3 kilo ohms. They're equal. And so when my current gets here, it's going to divide, and I'm going to have 4 milliamps going down this way, and I'll have 4 milliamps going down this way. So as my 4 milliamps go across the 1 kilo ohm resistor, so this 4 milliamps and that 1 kilo ohm resistor, our voltage is going to drop by 4. So 1K times 4 milli equals 4. So our voltage will drop by 4. So we have 8 volts right here. It was 12 minus 4. As our 4 milliamps goes through this 2 kilo ohm resistor, then it's going to drop by 8 volts. 4 times 2 is 8. It starts at 12, it drops 8. I'm going to have 4 volts here. So that tells me that this side of my capacitor is 8 volts and this side is 4 volts. So VC of 0 is 8 minus 4, or 4 volts. That was a lot of work to get VC of 0. Okay, so now let's look at VC at infinity. So at t equals 0, this switch opens. So when that switch opens, the whole rest of this circuit is not relevant. So at infinity, we just have this part left. So by infinity, our capacitor has completely discharged, and VC at infinity is 0. Okay, so it is also true that during the time period we're looking at, this is what our capacitor sees. It sees 1 kilo ohm, 2 kilo ohms, 2 kilo ohms, and 1 kilo ohm. And it sees two 3 kilo ohm resistors in parallel, and it turns out that it's the same numbers as we had before, but it's actually looking at two different things than we were looking at before. Because from the point of view of this capacitor, what it sees is that these two are in series and these two are in series, and that those are in parallel with the capacitor. So our equivalent is 3 kiloohms in parallel with 3 kiloohms, which is 1.5 kiloohms, but it kind of came from a slightly different place. So tau is RC, which is 1.5 kiloohms, times our capacitance was 10 microfarads. So 1.5 times 10 to the third times 10 times 10 to the negative 6 got me 0.015. And then 1 over tau was 66.667. And then V of t equals V of infinity plus V of 0 minus V at infinity, e to the minus 1 over tau times t. That's why we did all this. That's why we found V at infinity, which was 0. And V at 0, that's why we did all of this work up here, was to find V of 0. And then tau. So this is 0 plus VC at 0 was 4 minus 0 e to the minus 66.67 t, or 4e to the minus 66.67 t. Is that good? Questions?